Hello students, in this video we'll understand properties of the fundamental solution of the heat equation as it is an approximations identity. So let's recall, when we solved the heat equation, ut equals k uxx, with u of x0 being the Heaviside function, 1 for x greater than 0 and 0 for x less than 0, with that Heaviside initial data, we found the solution to this in self-similar coordinates. The solution to this was phi of x and t, which was 1/2 plus 1 over the square root of pi, the integral from 0 to x over the square root of 4kt e to the negative eta squared d eta, right? So that was the solution to this problem in self-similar coordinates. From this, we were able to define the fundamental solution to the heat equation, psi of x and t, which was d phi dx of x and t, which was the 2 goes away, and you have a 1 over 2 square root pi kt e to the negative x squared over 4kt like so. And we claimed, of course, when t goes to 0, what's happening over here? When t goes to 0, I have a 0 in the denominator and I have this e to the negative infinity, so that's going to be another 0, right? So I have 0 over 0. It doesn't quite make sense, right? So the behavior of this, so technically, strictly speaking, this is not defined for t equals 0. So note that psi of x0 is not defined, formally defined. But we want to think of phi of x0 really as a delta function, right? So what this really is but however, we think that psi of x0 is really a delta function, delta x, okay? All right, so let's prove that, okay? So how am I going to prove that? In other words, this means that this is an approximation identity. So mathematically, the family psi of xt for t greater than or equal to 0 is an approximations identity. Okay, excellent. Now what do I mean by that? Well, I mean the following. If I wanted to solve this problem over here, ut equals k uxx with u of x0 equals phi of x, what would I do? I would say that the solution to this problem is exactly u of xt is the integral over r of psi of x minus y t, comma phi of y dy, which is just the convolution of what? It's just the convolution of the function. It's psi convolution phi at the point x, comma, t like that, okay? It's the convolution of these two things, convolution. Okay, excellent. Good, and so now how do I prove this? Well, let's just follow our nose, right? So the integral over r of psi of x minus y, comma, t, phi of y dy is the integral over r of d by dx of the functions phi on top, phi capital, x minus y, comma, t. So d phi dx x minus y t, phi of y dy. Good. Now, of course, that's the same as the negative of the y derivative of this thing over here. Okay, so this is going to be the integral over r, negative integral over r d phi dy x minus y t, phi of y dy. Now let's integrate by parts. Assuming that phi is continuous with compact support, okay? Of course, I'm using this terminology because when I'm talking about distributions like the delta function, which is a distribution, I need to have a corresponding dual space, right? So in other words, what are distributions? They're continuous linear functionals on a space of very regular functions, like Schwarz functions or smooth functions with compact support. I'm just going to use this for simplicity to make my calculation work out nicely, okay? All right, so if I do that, what will we get? We'll get the integral over R of phi of x minus y comma t, right? And then phi prime dy. And plus the boundary terms, right? Plus the boundary terms. Which are 0 by the compact support. Because we're integrating from negative infinity to infinity, okay? Now, of course, when we plug in t equals 0, so as t goes to 0, so the limit as t goes to 0, integral over R of phi of x minus y comma t, phi of y dy, and phi prime of y, of course, right? Now, of course, I'm going to interchange the limits and the integrals over here, and then this becomes what? Well, phi is only going to be what? Phi of x0 is going to be 1 only when x is positive. So this is going to turn into what? Turn into the integral from negative infinity up to x, because y can be no more. Up to that point, we get positive values, and once you're beyond x, we get negative values. We don't want those, right? We can't have those. Phi prime of y dy. And by the fundamental theorem of calculus, is just phi of x. Perfect. So in other words, what is u of x0? U of x0 is phi of x. In other words, it completely solves this problem. So that's what I mean by approximation to identity, is that taking this limit over here is the fact that, in some sense, the derivative of the Heaviside function is this delta function. So I'm really leaning to the fact that we have a Heaviside function as an antiderivative of this value of psi of x0 in some sense, in some weak sense. And I'm allowed that to pass the limit and interchange limits in integration. The important thing here is that when you're dealing with partial differential equations, you initially have to assume that there's some regularity to start, right? Otherwise, you can't even get your hands on the problem because a PDE necessarily involves taking a function and doing derivatives of it. This gives us an illustration. In fact, there's something deeper in the behind the scenes over here, is that there's some ideas behind distribution theory in order to try to find out what the fundamental structure of these solutions are. So in further videos, we're really going to try to sort of focus in on how we find these fundamental solutions, because the fundamental solutions give rise to distribution theory and allow us to prove actually some weak results, and that weak results sometimes imply strong results. Thank you very much.